Bohr was trying to explain the Rydberg formula for the spectrum of hydrogen, and he was starting with the Rutherford model. Now, the Rutherford model has a nucleus in the center, a positively charged nucleus, and an electron going around the outside. And hydrogen just has one electron, which makes it nice and simple. And if they're going around in circular orbits, then by assuming that the electric force is equal to the mass times the acceleration, and the acceleration, if it's going in a circle, must be the centripetal acceleration, then equating those two things tells us the relationship between the velocity, or the speed of rotation of the electron, and its radius. But Bohr knew that since the light being absorbed or emitted by this atom had to come at very specific frequencies, then it also had to have very specific energies because of the relationship between the photon's energy and its frequency. And that energy had to come from the atom itself. And so therefore, when the photon was coming away from the atom with a certain amount of energy, the atom had to have changed by that amount of energy. And so if only specific energies of photons were being emitted, then only certain changes in energy were permitted inside the atom. And in much the same way that Planck and Einstein had to restrict the possible energies of photons to integer multiples of certain amounts, Bohr found that he could explain the Rydberg formula if he restricted the product of mv and r, which for a circular orbit is known as the angular momentum, to be a multiple of h on 2 pi. And h on 2 pi is such a common number used in quantum mechanics that it's now called h bar. And it's written like this. And a completely embarrassing personal aside, I once accidentally wrote on a birthday card, habits can be hard to break. But like the other pioneers of quantum mechanics, Bohr was being quite revolutionary in breaking habits of his. Assuming the angular momentum, which we normally denote as L, can only take particular discrete values out of the entire continuum, was an extremely revolutionary concept. Bohr had no motivation for it other than he needed to do it in order to explain the emission and absorption lines from hydrogen. So let's see how he got the result he wanted. Remember that for a circular orbit, the angular momentum is just the momentum times the radius, and linear momentum is just mass times velocity. So that's going to be quantized in units of h bar. And what we have is we have one equation here and two unknowns, velocity and radius. Fortunately, we have another equation over here, and if we've got two equations and two unknowns, then we know we can solve it. So let's do it. So we simply rearranged the first equation to get velocity in terms of the radius, and then substituted that into the other equation. So now we just have a single equation for the radius, and so we've got the values of the radius. And if we cross out the mass and the radius from the top and the bottom line, so the radius gets bigger in discrete amounts as n gets larger. The very smallest it can be is when n equals 1, and so then the radius would be h bar squared on mke squared, and that's called the Bohr radius. Now we could solve for the velocities if we wanted to and get them as a function of n as well, but what we're really after here is to try and figure out the energies that the electron can take around the proton, because it's changes between those energies, those possible energies that the electron can have, that's giving the photon that's being emitted particular energies, and that photon having a particular energy means that the photon has a particular frequency. So these discrete frequencies are coming out of the energy levels for the electrons. Now there's two kinds of energy for the electron, kinetic energy and potential energy. Now the kinetic energy is just half mv squared, just like it normally is when we don't worry about relativity. Potential energy, well, the force is attractive and is going as 1 on r squared, so the potential energy goes as 1 on r, and because the energy has to go up as they get pulled apart, there actually has to be a minus sign there. So to deal with the kinetic energy part, we notice that we have an mv squared up in that equation, so that's going to make that easier. Then those two terms look almost the same, and so you're just going to end up with, so the fact that we have quantized radii means we're going to have quantized energy. So we just substitute that radius into the energy and we get, so the electron has these discrete radii with discrete energies, and each possible state is characterized by a number n. So these two states here might have n1, this one up here, that's a different state the electron can be in, that might be n2. And so what Bohr said was that this electron can't just emit radiation and decay because it can only be in these particular levels. And so in order to emit a photon, it has to make a transition from one level to another level. And when it does that, it's going to change its energy in a very discrete amount, the difference between En2 and En1. And when it does that, it's going to emit a photon with that energy. And because that energy difference is going to be something times 1 on n1 squared minus 1 on n2 squared, then the frequency, since the frequency is just proportional to the energy, we're going to get the Rydberg formula coming out of that. And so that's why Bohr's assumption gave him the Rydberg formula. And so Bohr's model worked. It explained why people saw discrete lines in spectra, and it gave quantitative reasons for why the particular lines were there in terms of fundamental parameters rather than just some experimentally determined constant. But like Planck before him, Bohr didn't really change his idea of what electrons were. He just invented a crazy rule that got him the right answers. And just as Einstein took Planck's ideas about light and really changed our model for light to invent the photon, in 1924 de Broglie did the opposite, and he took Bohr's rule and he changed our ideas about all of matter.